Alright, we're going to begin with section 15.3 in this video, which is the fundamental theorem of line integrals. Fundamental theorem of line integrals FTLI. Alright, so let C be a smooth oriented curve from x naught, y naught, z naught to x1, y1, z1 with vector function r of t where t is between a and b. Let f be a differentiable function such that the gradient of f is continuous on C. Then the line integral over C of the gradient vector field. So we're doing a line integral of a vector field. It just happens to just so happens, that vector field is the gradient of some scalar function f dot dr equals f of r of b minus f of r of a. And notice that t varies from a to b, so r of b is the end point of the curve and r of a is the start point of the curve. So that's just x1, y1, z1 is r of b, x naught, y naught, z naught is r of a. So this equals f of x1, comma, y1, comma, z1 minus f of x naught, comma, y naught, comma, z naught. So in some problems you'll see it this way because you'll already be given what r of b and r of a are, those values, or you just may have to find these points. But either way, it's going to make evaluating, and this fundamental theorem of line integrals, it's going to make evaluating integrals of this type a lot easier, because all we're going to have to do is, we know that potential function f, and we just take the endpoints of our curve C and we put them into the potential function and take the difference. So thus, if the vector field f is a conservative vector field, with potential function f then the line integral over C of the vector field f dot dr gives us this exact same thing that we have here. So equals the potential function f evaluated at r of b minus the potential function f evaluated at R of A. So now I can summarize why this is important and why it's useful here. So the line integral over C of f dot dr is only dependent upon the endpoints of C and is independent of the path traveled by C. That is, conservative vector fields are independent of path. So one big key thing for us is that when we were doing a line integral of a vector function over some curve C previously, we always had to parameterize the curve C and then take that parameterization of C and substitute it into F. We don't, although we see it here, we actually don't have to parameterize C anymore. All we need are the start and end points of the curve, and that's it. We don't need a parameterization of the curve because it doesn't matter what the curve looks like because it's independent of path. So we could be going from whatever one point to another along a straight line and one point to another along some complicated curve. But as long as our start and end points are the same, you're going to get the exact same thing for this integral regardless of how that curve looks. All right, so key implication for us is that there's no need to parameterize C. And to kind of reiterate that, I'm going to go back because up here when I wrote f of x1, y1, z1 minus f of x naught, y naught, z naught, and you see that there's no parameterization there. Here, we may look at that as the parameterization been done, same thing here, but it's not necessary. So we can rewrite this as f of x1, comma, y1, comma, z1 minus f of x naught, comma, y naught, comma, z naught. So f evaluated at your endpoint minus f evaluated at your start point. All right, so let's look at, we're going to look at some things that are equivalent to being independent of path, so we can determine whether we have a line that was independent of path or not without having to use anything that's new from what we've been doing. So under the proper conditions, it follows from the fundamental theorem of line integrals that the following four statements are equivalent to each other? No, I didn't. We talked about, when I say proper conditions, we talked about those. I just didn't restate them here because there's only two key aspects I'm going to be focused on. With those proper conditions were just that our vector field that we're talking about is defined everywhere, and that the partials of our vector, the functions in our vector field, are continuous. So we discussed those conditions in section 15.1 and 15.2. All right, so the four things that are equivalent are: one, vector field F is conservative. And again, I want to reiterate here that F is conservative does not mean that the curl of F is equal to 0. Now that's what we looked at. We look at a lot when we're trying to figure out if a vector field is conservative, and that's going to be one of the things that's in this list. But to be conservative just means that the vector field F is equal to the gradient of some scalar function F. So that's what this means by definition. But it is equivalent to the curl of F being equal to the 0 vector under those conditions. So second thing is the line integral over C of F dot dr is independent of path. Third is that the line integral over C of F dot dr equals 0 for every smooth closed oriented curve C in the domain of the vector field F. So if closed curve, that means that our curve C, the start and end point are the same point. If that's the case, then we have the line integral over C of F dot dr is equal to 0. Is the same as being independent of path, and the same as the vector field F being conservative. And then lastly, it's the same as what we've seen most regularly, the curl of the vector field F being equal to the 0 vector. So for our purposes, what we've used up to this point are the F being conservative and curl of F being equal to 0. We're going to now use the curl of F equal to 0 along with number 2 up here being independent of path. And then we'll use 3 in section 15.4. We'll see that used some in that section. Now, what we're going to end up doing is we want to evaluate this integral, but we're going to want to evaluate it without having to use the curve C. But what we're going to need to do is figure out, can we do that? So the approach we use to figure out, can we evaluate this integral without having to parameterize C, is first we're going to evaluate the curl of F and make sure it's the 0 vector. And then we know that we don't have to parameterize C. We can find some scalar function and then use the fundamental theorem of line integrals. All right, so I'm going to stop this video here, and then in the next video we'll do an example where we actually see how to use this information.